So the next portion is about pH scale, and we have already learned last year what pH scale is. pH scale is generally a measure is a measure of acidity. So what do I mean by that? It is basically how acidic a substance is. In last year when we learned it, we saw that the scale is from 1 to 14. So this year, if you look at this set of notes, it says it's from 0 to 14. And it really depends on what is the book that you're looking at. Some books will say still that it's 1 to 14. Some books will say that it's 0 to 14. And actually, both of them are correct. Okay, and in this whole scale, our midpoint is 7. So 7 is when it is neutral. And example of a neutral substance, we will all know that it is water. Okay, but later on, you also need to know that salts are also neutral. And salts, for example, is a product of an acid plus alkali reaction, which we know that is a neutralization reaction. In a neutralization reaction, all the products of that reaction got to have a neutral pH in order for it to be called neutralization reaction, right? So that is why from there we can see that salts are neutral. So our sodium chloride salt, our potassium chloride, potassium nitrate, all those things, they are all neutral pH. Okay, so moving down the pH scale, when we move on to the smaller numbers, this will be when a substance is the most acidic, and moving up the scale, this is when the substance is most basic. Okay, and so yeah, I think this is quite straightforward. Okay, some people may be wondering, is there anything stronger, is there anything that is extremely acidic, or is there any acid that is at pH 0, or is there even negative pH? I have included a video later at the bottom of the SLS page where you see about super acids. So do check out that video. It's actually quite interesting to find out about acids that are even more acidic than the regular ones that we see in that we commonly know of, like our sulfuric acid and so on. So super acids is a interesting concept. Okay, so over here we have the pH of common substances. And is there anything that is out of the ordinary for you? Coca-Cola. Coca-Cola, we all know that it is acidic. Drinking too much of it will cause your teeth or tooth enamel to get corroded. Okay, because that is a acid and carbonate reaction. Okay, egg whites are actually acidic. That's interesting. Sorry, egg whites are alkaline, basic. So that's a bit interesting. Milk is slightly acidic. Vinegar is ethanoic acid, which is no surprise at all that it's acidic. Okay, so these are pH of common substances. You don't have to memorize anything at all. It's just for your info. Now, what exactly is pH? This page over here is more so for your information if you are interested. All right, and we said just now that pH is a measure of acidity. And even if a substance is basic, we can still determine its pH. Okay, and so if didn't we just say that it's a measure of acidity, then what about things that are basic? How can we say that it is a measure of acidity? And what exactly is pH? Last year, those of you in my class, I've shared with you how to calculate pH. Right, pH has a simple calculation, which is this. pH is equals to minus log base 10, and the square bracket over here, okay, this stands for concentration of hydrogen ion. Okay, you may want to write this down, which is just meaning how much hydrogen ions there are present in this solution. So what you see on this slide over here is the opposite. it is showing you how to calculate, how to determine the concentration from the pH of a solution. So if I have something of pH 1, it means that it is 10 to the power of minus 1 moles, mole per dm cube of hydrogen ions. This unit is, we call it molarity, or we call it mole per dm cube. It's basically a measure of how much hydrogen ions are present in per unit volume of solution. So 10 to the power of minus 1 over here is just 0.1, right? What about 10 to the power minus 7? This is where it is, there are 7 zeros in front of it. So this is actually 0.002345677. Yeah, this is how much hydrogen ions are present. pH 10, which is an alkaline or basic solution, this has 10 zeros inside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 1. This should be 1. Yeah, this is how much hydrogen ions that's inside that solution of pH 10. Wait a minute, didn't we just say that this is an alkaline solution? Why are there hydrogen ions inside? Okay, so this leads me to introduce to you this idea. For us to be able to calculate pH values, hydrogen ions must be present in the solution. So even if I have a pH of 14, there are still hydrogen ions that are present. However, you will see that it has very, very much lesser hydrogen ions compared to something which is of pH 1. So what exactly are we comparing? Okay, we are comparing actually the concentration of hydrogen ions with the concentration of hydroxide ions in any solution. Even for a neutral solution as well, we're comparing how much hydrogen ions are present compared to how much hydroxide ions are present. So in a neutral solution, in an acidic solution, an alkaline solution, why are there both hydrogen ions and hydroxide ions present? Okay, perhaps let's take the example of hydrochloric acid. So dilute hydrochloric acid, it would have water present. It would also have hydrogen ion and chloride ion present. This water, the water over here, is allowed to dissociate into hydrogen ions and hydroxide ions. So this is where you get hydrogen ions and hydroxide ions present inside a solution of hydrochloric acid. Okay, you have hydrogen ions present, you also have hydroxide ion present. And hence, in an acidic solution, I have very much more hydrogen ions compared to hydroxide ions. In a neutral solution, let's say I have sodium chloride solution, so NaCl aqueous, right? NaCl aqueous, of course, I'm not going to be able to get hydrogen ions or hydroxide ions from NaCl itself, but from the aqueous portion, which is water, I can have H plus and OH minus, and the concentration of these two should be equal to each other, which is why it is neutral. All right, and then for an alkaline solution, perhaps let us talk about sodium hydroxide aqueous. Okay, in sodium hydroxide itself, I have Na plus, OH minus. From the water, I have H plus and OH minus. So you can see that I have a lot more of hydroxide ions versus hydrogen ion, right, which is coherent with what we are seeing over here. More hydroxide ions than hydrogen ions. Okay, so this table over here is useful for you to quickly determine if a substance is acidic, neutral or alkaline based on how much hydrogen ions and hydroxide ions are present in it. Okay, so that is the relationship to the pH scale. The next portion of it is indicators. There are mainly four types of indicators that are seen. Okay, litmus, one, methyl orange. Third one is phenolphthalein, but please note that phenolphthalein is not in syllabus. This was in syllabus perhaps maybe about five years ago. Okay, but it's no longer in syllabus because it is a known carcinogen, right? It causes cancer. The other common litmus that we need to know is universal indicator. So actually, in terms of the color changes, I don't think I need to go through with you again because litmus, you have it as red and blue. There's only two colors. It can only tell you whether is it acidic or alkaline or basic rather. Right? It cannot tell you whether is what's the exact value of it. Methyl orange is also another indicator that is slightly similar. However, there is an additional color that is in the middle, which is orange. All right, and again, it gives you a rough range of pH that falls under a certain color observation. So red, orange, yellow. Phenolphthalein, similar idea, but it's not in syllabus anymore. For universal indicator, we have seen last year that it follows the rainbow color sequence. So please memorize your rainbow colors again. You can use your Roy G. Biv. And please note that green is for pH 7. And how do we use a universal indicator is that the colors must be compared to a color chart. So that's where we match and come up with the rough pH value for that solution. Okay, so generally the advantage of using a universal indicator over litmus is that it shows you this gradation in color change, right? There is this constant change in color, which shows you the slow change from an acid to a neutral solution to an alkaline solution. Okay, so we are able to determine the exact or rough, or if not the rough value of the solution. Okay, other indicators you can only determine if it's acidic or alkaline. That's all. One disadvantage about this universal indicator is not so much about the use of it, but is a wrong match for a process. Universal indicator is not suitable for this process called titration. Titration is a process to determine how much of an acid, let's say, is required to neutralize a known concentration and volume of an alkali. Let me give you an example. If I have hydrochloric acid, and hydrochloric acid is colorless in appearance. Alkali, let's say sodium hydroxide, it is also colorless in appearance. If I want to know how much acid is required to neutralize this certain volume of sodium hydroxide, I wouldn't know by just mixing the both of them together, because what I will end up getting is sodium chloride, which has also a colorless appearance, and water, which is also colorless. So in this entire reaction, the only thing that I'll see is a colorless solution, nothing else. So how would I know what would be the volume of hydrochloric acid required to neutralize, let's say, 25 cm cube of sodium hydroxide? This, our context over here, is a neutralization reaction, right? I wouldn't be able to determine the volume of hydrochloric acid required? Because in this case, everything that I see is colorless, which is why in such a scenario, if I want to determine what is the volume of acid required, I'll need to be able to have a very clear observable change, right? And the observable change over here has to come from an indicator, because the indicator when added is able to let you see when is it acidic, when is it neutral, when is it alkaline. So a good indicate anything an indicator must be used in this. But why is it that universal indicator is not suitable? If you go back to the colors of the universal indicator, so let's say we start with hydrochloric acid. Hydrochloric acid has a known pH of about pH 1 to 2. Okay, and sodium hydroxide has a known pH of about 13 to 14. In order for it to be neutralized, it must come to the neutral pH, and the neutral pH is green, is 7, and I should, if let's say I'm using universal indicator, I should see it turning green. But when you look at this, the green over here is a spectrum of colors. There is this spectrum of gradation of colors. In doing a titration process, it is difficult to determine what is the correct shade of green that is precisely pH 7. Hence, it is very difficult for us to use universal indicator because you are constantly seeing a color change. Whereas if I'm using an indicator, say methyl orange, if I'm using methyl orange, when I'm using hydrochloric acid, I would see it as red. So imagine I have sodium hydroxide inside a conical flask, and I'm and as I'm adding hydrochloric acid to it, it will slowly move from the yellow color all the way to orange color. And once I see that one drop of the solution is able to change the entire solution to orange, I know that I have neutralized the solution. Okay, more about this is in more of this and a visual demonstration of what titration really looks like is included in the video later. So please check out the video to see it in greater detail. Okay, so this is what we're talking about over here. Why is universal indicator not suitable for titration? Because it does not have a sharp color change. It does not have a sharp color change. There is this constant changing of colors that it is difficult to determine what is the endpoint neutralization in the titration process. So I cannot determine what exactly is the correct shade of green that allows me to get the neutral pH. Okay, so when I'm measuring, so moving on, when I'm measuring pH of a solution, generally I have two ways. One is using a universal indicator and comparing it with color chart. The other one is a digital process, pH meter. So over here we have a pH probe. This thing over here is a pH probe that I will insert into the solution, and then it will show me my pH. Universal indicator, last year when you have used it before for practical, you will realize that sometimes it's a bit difficult to determine exactly whether is it light orange, orange, or even maybe yellow. Or sometimes for the blues, it can be a bit difficult to match to the correct color. So sometimes using the universal indicator, it gives you a rough value of a pH. It is difficult to give you the exact value of a pH, which is why scientists usually they just use a pH meter, straightforward. Okay, so um, when we see a pH curve, it looks something like this.